Hello, you are welcome to this class. In this class, we're going to continue with our discussion on Graham's law of diffusion. In the previous class, we defined Graham's law of diffusion and we gave some examples for solving calculations involving Graham's law of diffusion. We also solved some examples. The purpose of this class is to bring the formulas involved in Graham's law of diffusion and make them clearer, showing you where each of the formulas can be used to solve problems involving Graham's law of diffusion. The first formula that we're going to talk about is R1 over R2 is equal to root D2 over root D1. This formula is used when we are given the rate of diffusion of the gases and density of the gases. When we are given the rate of diffusion of the gases and the density of the gases, we use this formula. In most cases, we'll be given three of these parameters and then we are asked to look for the fourth parameter. Second, when we have another formula R1, R2 over M2 over root M1, this formula is used when we are given the rate of diffusion of the gases and then the molecular masses of the gases. In this case, most of the times, we are not always given the molecular masses of the gases directly. We may be given the atomic masses of the molecules involved, the atomic masses of the atoms of the molecules involved, and then we are given the rate of the diffusion of the gases. So if we have that, we can calculate the molecular mass of the gases by using their atomic masses. Here, when we are given the rate of diffusion and molecular masses, we use this formula. The next formula, when we are given the time of the gases and density of the gas, maybe we are given the time of gas 1 and 2 density, and then we are asked to calculate the fourth, that is second time. We use T2 over T1 is equal to root of D2 over root of D1. I say that in this case, we are given time of the gases and then we are asked to look for the maybe density, one of the density, just any three of these parameters will be given to us and then we are asked to look for the fourth parameter. But note that in this case, V, the volume of the gases involved must be equal for us to use this formula. If the volume of the gases are equal, we use this formula to calculate the unknown time or unknown density. V1 must be equal to V2 for us to use this formula. Now, if V1 is not equal to V2, we use V1 over T1 over V2 over T2. This is equal to root of density of gas 1, root of density of gas 1 over root of density of gas 2 over root of density of gas 1 of gas 1. So in this case, V1 is not equal to V2. So we have the density of the gases and we are given different volumes for the gas and time. We use this formula. Then we can also have that T2 over T1 is equal to molecular mass of gas 2 over molecular mass of gas 1. In this case, we are given time and molecular mass, or we may be given the atomic masses of the atoms in the molecules involved, and then we are asked to calculate one of these parameters. In this case, we use the atomic masses to calculate the molecular masses of the molecules, and then we look for the parameter that is missing in these four items involved. But note that in this case, V1 must be equal to V2, just like we have in this case. When the volume of the gases are equal and we are looking for either time or molecular mass, then we use this formula. Then when the volumes of the gases are not equal and we are also looking for time, either time or molecular mass, then we use this formula, that V1 over T1 over V2 over T2 is equal to molecular mass of gas 2 over molecular mass of gas 1. So these are different formulas that we use in solving problems involving Graham's law of diffusion, and different things that we warrant you to use each of the formulas. For example, if we have that example, if we are given that hydrogen gas 300, if we are given that 300 cm cube of hydrogen gas diffuses through a port, diffuses through a porous port, diffuses through a porous port in 50 seconds. In 50 seconds, how long will it take? Will it take 100 cm cube of oxygen gas to diffuse through the same port, through the ports? Now we may be given that oxygen is equal to 16 and hydrogen is equal to 1. That is the atomic masses of oxygen and then hydrogen. How do we solve this? To solve this, we bring out the parameters given to us. We are given V of hydrogen to be 300 cm cube and V of oxygen to be 100 cm cube. We are given the time of hydrogen to be 50 cm cube, 60 seconds, and we are looking for the time of diffusion of oxygen. Then the molecular mass of hydrogen gas M2 is 2 times by 1, which is 2, and molecular mass of oxygen molecule is 2 times by 16, which is 32. Now looking at this, we have different volumes. This is 300 here and this is 100 in this place. So the formula we are going to use is the one that involves molecular masses and different volumes. What we are going to do there is that we compare the volume. First of all, we are going to get 2 times. The first time we are getting, when we solve it the first time, we are getting the time that is equivalent for diffusion of oxygen for this 300. And then we now use that one to solve or to predict the time for diffusion of 100 cm cube of the gas. Let's solve it. The formula when we are given different volumes of the gases and molecular mass is V1 over T1 over V2 over T2 is equal to molecular mass of gas 2 over molecular mass of gas 1. Now this means that V1 which we have as hydrogen, we have our hydrogen which is 300, can have 300 or we can start with oxygen. We have that V1, that's hydrogen, 300 over T2, T1 is 50, then this over V1, V2 is 100, then over time for this we don't know, then this is equal to molecular mass of oxygen root 32 over root 2, that is M2 over M1. Here V1 is hydrogen, 1 is hydrogen, Y2 is oxygen. So wherever we have 1, we put the value for hydrogen, and wherever we have 2, we put the value for oxygen. So it becomes this. Now we solve for this. We have that 300 over 50. Here, this is division, separating this and this. So we can change this sign to multiplication. And if we are changing it to multiplication, then we are going to invert these values here. So we have this multiplied by T of 100 is equal to root 32 over 2 over root 2, and so we have that if we have this, we can cancel this. So we have that 3 over 50 times by T is equal to root of 32 over 2, and so what we're going to have is that 3T over 50 is equal to 3T over 50 is equal to, this is root 32 over 2 is 16 over 1. So we are going to have that 3T over 50 is equal to root 16 over root 1, root 16 over root 1. So we are going to have that 3T is equal to 3T over 50 is equal to root 16 is 4 over root 1 is 1 over 1. So we are getting that 3T is equal to 3T is equal to 200. Yes, 3T is equal to this times this or this, so we have that T is equal to 200 over 3, 200 over 3, that will give us 200 over 3 will give us 66. That will give us 66.67, 66.67. This is the value for the time we are looking for. This is T of oxygen, T of oxygen gas that we are looking for. T of oxygen gas that we are looking for is this. So this is how to solve it.